augmented reality is presented to our senses through specialized output devices that address one or more of our senses. This is ever more immersive when our body motion is reflected in the virtual environment, thus the need for input devices that track our motions. In this chapter, we will explore the devices that can trick our senses and track our bodies, grouping them by the addressed sense. For each of them, we will explore their functionality, use cases, weaker points, and, where applicable, the potential risks they pose. We are starting with one of the largest devices in our list. Caves are similar in technology with what you can see in 3D cinema, except that instead of have a huge display in front of your eyes, you're in a room with the walls being actual displays. Depending on the setup, it can have between 3 and 6 displays. The 4 displays setup in the image on the left is a popular one as it covers the user's field of view and addresses, leaving out the least likely areas to be involved in the simulation, above and behind. In the image on the right, there is also a behind wall which swings on hinges to allow access. In other setups, the entry wall is fixed but has a door cut in it. The displays are translucent glass walls on which dedicated high-performance projectors display the virtual scene. This leads to quite large space requirements, as each projector is at a distance comparable to the size of the cave. The projector for the floor display in the image on the left is above, which causes dense shadows that obstruct the image. To avoid this, the projector must be underneath the cave, which requires a room on the lower floor or in the basement. The walls display stereo images, which makes them appear blurred to the naked eye, but to the user wearing 3D glasses will appear to have depth. Caves are wonderfully immersive intrinsically, since the user is physically in the middle of the virtual world. There are, however, a few situations where the illusion breaks. Consider the waves in the image on the left and how they span multiple displays. At the corners of the room, they look unnaturally bent thanks to the physical bend in the display. This situation is solved by tracking the user head and adjusting the image to look right from where the user is looking. This means that while there can be many users inside a cave, only one can see the image without artifacts. Another break in presence can appear when reaching toward objects close to us, only to realize that they are rendered on the wall, and the hand obstructs them. Besides the breaks in presence mentioned above, the caves can also cause dizziness and loss of balance. This can happen either when the stereo rendering is not properly calibrated or when the scene is very dynamic. Think riding a roller coaster, creating a discrepancy between the visual and the proprioception senses as based on what it sees. The body tries to anticipate and adapt to forces and accelerations that are not there. The head-mounted displays, HMD, are the most popular devices on the VR market. Small enough for home usage, performant enough for lab usage, they are basically wearable high-resolution monitors that cover a large proportion of the field of view, the rest of it being obstructed by the opaque sides of the goggles. HMDs have been produced, at least for research projects, since before LED panels were available, resulting in quite heavy and difficult-to-bear devices. Even after LED technology became available, the field of view offered by HDMs was quite limited, the user experience being of viewing the virtual world through a keyhole, the peripheral vision being simply obstructed by the sides of the device. Gradual improvements in technology led to 93-degree device, which offer a remarkable 93-degree field of view coverage. Traditionally, the HMDs are connected to a graphical workstation that renders the virtual world through either wired or wireless connections. The wired connection is cumbersome and brings the risk of getting tangled in the cables, while the wireless connection may cause delays and lower display quality. More recent devices are moving away from the connection with a workstation and act as mobile devices that run and render the virtual environment. These HMD provide the user with an online connection and a game portal, essentially become a mobile gaming station. The user wearing an HMD can only see the virtual/mixed reality environment. Natural exploration of the virtual environment demands that head turns and motions result in the proper update of the virtual environment displayed in the HMD. For instance, if the user turns the head to the left, the displayed image must rotate to the right so that the user sees the expected area. This requires fast and accurate head tracking, which we will discuss soon. The device also presents a forward-looking camera that can display the real environment on the displays in front of the user eyes, thus supporting not only virtual reality, but mixed reality as well. The immersion provided by modern HMDs is excellent, but there are still possible breaks in presence and risks. The HMD field of view is obstructed towards the vision periphery, which raises the risks of tripping on furniture or other objects in the room. This is mitigated by manufacturers by supporting the definition of room boundaries such that the HMD can warn you when you are nearing them. When using a wired HMD, this risk is increased by the possibility of getting tangled with the cables. The instinctive quick motions of the head make the strobing, smearing, and judder effects discussed in the previous chapter more probable. Such effects can quickly lead to dizziness and even loss of balance. Finally, another aspect that can break presence is the screen door effect. The HMD displays are very close to the user eye, which makes it possible to see and distinguish their physical pixels, as seen in the image at the bottom left. This results in seeing the scene through a net or screen door, hence the name of the effect. The previous HMDs were more oriented toward virtual reality. The HMDs here are oriented toward mixed reality. You can tell that by their features for providing a view of the real world, either multiple cameras or non-opaque displays. The HMDs on the left are recent offerings by Meta and Vive. Both rely on opaque displays on which front-facing cameras can display a real-world view. Their functioning, limitations, and risks are similar to the VR HMDs. The device on the right, the Microsoft HoloLens, is an innovative that uses a transparent screen through which the user can see the real world directly. There is no limitation on the peripheral vision, so the safety risks of the previously discussed HMDs are not applicable here. The HoloLens relies on MEMS lasers to display the image on the transparent screen through which the user is seeing the environment around. The resulting view of the virtual environment is usually somewhat faded, depends on the room's lighting level, and requires deliberate focus to see it. For users who do not want to invest in expensive HMDs, there are low-cost solutions that allow using a cell phone as display. The phone display is split in two halves, each rendering the scene for one of the eyes, with the necessary displacement to achieve stereo vision. The cell phone is then encased in an HMD-like frame that can be made even from cardboard, the name of the original solution offered by Google. The head tracking for these devices is provided by the phone inertial sensor, which is likely to accumulate errors and require periodical recalibration. The complexity of the virtual environments for such a setup is naturally reduced due to the limited computing power provided by the phone. This can also lead to strobing, smearing, and judder. A lower cell phone display resolution can also cause a screen door effect. Motion tracking is essential for interacting intuitively and naturally with virtual environments. While mouse and keyboard navigation and interaction are handily available to everyone, they are no substitute for the immersion created by turning your head to see something instead of pressing a key. Motion tracking is applicable to all body parts, but we will start with head tracking as it has the largest impact. HMDs usually rely on inertial measurements units to provide fast changes in head motion acceleration. Inertial sensors accumulate errors over time, resulting in wrong measurements. This is corrected using slower, but still quite fast, absolute position sensors that provide accurate positioning. In the case of the device on the left, the HMD is accompanied by two devices that flood the room in IR light that bounces off the retroreflective markers positioned. The IR light reflected by the several markers is then received and used to calculate the position and orientation of the HMD. You may have noticed that the retroreflective markers are not placed only on the HMD, but also on the tracker in the lower left corner of the image on the left. Multiple such trackers can be attached to any body part within comfort limits, supporting more complex interaction metaphors with the virtual world. While not very visible in the image, the retroreflective markers are present also on the two controllers placed in front of the HMD. The stereo goggles on the right is tracked using a configuration of IR markers mounted on its frame. Notice how the placement of the IR markers is not symmetrical. This tracking mechanism relies on IR cameras, feeding the video of the tracked device to the workstation running the simulation. The IR markers are very bright in IR light, so image processing can detect them easily in the video frames. The multi-source video streams are then converted into a stream of positions and orientations. The asymmetrical placement of the IR markers is essential for determining the left-right, front-back, and up-down orientation of the goggles. The direction of gaze is a modality little used by humans to interact with the real world, save for rare cases when they signal something. However, the direction of gaze is quite an input for others, as they understand where is the focus of a person. Think of how aware we are when somebody is staring at us. Gaze tracking in virtual reality follow the same lines of applicability, measure where the user is looking, and learn about behavioral, cognitive, attentional, and perceptual mechanisms. The eye tracking is usually done using pairs of IR LED and camera mounted inside the HMD around the lens and pointing toward the eye. The IR light emitted by the LED is reflected by the human eye, and the camera records the reflected light. The camera output is then used to infer the direction in which each eye is looking and thus determine the focal point of the gaze. Rendering sound to a user's ears is a problem long solved. The most common devices to accomplish this are the headphones. Users can either plug into the workstation running the simulation regular headphones like you can see in the image on the right, or rely on the HMD built-in headphones as seen in the image on the left. Besides the basic stereo headphones, more recent headphones offer spatial sound, which is similar to have a surround sound system like you do in a cinema or home theater. Although, the headphone have the same basic design with a small speakers in /over/ on each ear. The spatial sound is achieved using audio filters that make the sound bounce off the ears, similarly to how it happened in the real world. One limitation of using headphones is the lack of deep bass. Think of a large church bell tolling close by or a huge truck passing by. Both create a low vibration which you can sense in your bones. A virtual scene lacking such sounds will feel empty to users who have experienced similar situations in the real world. The sense of smell is a very powerful catalyst for achieving presence, and consequently, there are continuous attempts to simulate it. Taste, on the other hand, is rarely used outside eating and consequently rarely involved in XR simulations. The most basic solution to adding smell to a virtual environment is to place the necessary ingredients/aroma next to the user. Because smell tends to linger, it is difficult to switch between smells, and often such attempts result in mixed odors whose combination effectively stinks and, if too intense, will make the room unusable without venting it. Artificial smells are created using cartridges containing substances with various smells. Users can purchase such cartridges and install a selection in devices connected to the virtual environment. Upon entering an area exhibiting a certain smell, the XR application would activate the release of the appropriate cartridge. The image presents a recent device for rendering smell and taste. Releasing the smell in the small enclosure in front of the user's nose and mouth makes it easy to vent when the smell needs to change. Also, such a small chamber requires very little substance, so venting it will not impact much the overall room air quality. Tactile feedback has been available for a very long while in numerous devices, not in the least the cell phones that we use every day. The feedback is created with vibrations of various frequencies that can simulate surface rugosity or even little impacts, such as pressing a button. The controllers on the left that are among many VR/XR devices that provide such feedback. The hardware behind the vibration are little motors like those on the right, having half cylinders attached to their shafts. The half cylinders are off-axis weights that, when rotated, pull the motor to the side, thus creating the vibrations. These motors have a very low response time, allowing control of vibration both as on-off as well as in frequency. To create tactile feedback, XR applications only need to activate the motors upon contact between virtual objects and the user's avatar. Force feedback is a very challenging area of virtual reality due to complexity, sensitivity, and span of the human proprioceptive sense. We perceive forces with our entire body as forces effect. Even small ones tend to impact our entire body. Designing hardware that can render forces that cover the complexity of our sensing is impossible with today's technology. The approach taken by researchers and businesses is to address localized force feedback, in its majority focused on the hand. A major aspect of force feedback is safety. In day-to-day life, we apply significant forces on the environment. Force feedback devices apply forces to the human body, trying to simulate the reaction forces applied by the environment. Applying high forces to the human body as part of a simulation raises serious risks of injury because the user is usually not prepared to receive the force. Finally, the response time of the force feedback devices must be extremely short while working with very high forces. As a basic example, when sitting down, we apply a very high force on the chair in fraction of a second. When sitting up, we remove that force just as fast. Consider kicking a ball or opening a stuck bottle cap. Both require high forces, but different in nature. Kicking a ball is a short duration impact, while opening the bottle is a gradual effort. Both impact the entire body, as the skeleton and the muscles need to provide counterbalance for the main impact point. In both cases, rendering the force to a user that is not prepared for them will result in delayed counterreaction and possibly injury. The hardware response time is influenced by the following factors: body tracking delay, virtual avatar interaction calculation with virtual objects, delay of the force feedback device in applying the force commanded by the VR application. If all these summed together are above a few milliseconds, the user will prepare for the force feedback impact but not receive it when expected. Consequently, the user relaxes, and just then, the force feedback is applied, leading to confusion. The phantom haptic devices shown here offer extremely accurate and realistic force feedback. The virtual environment interaction metaphor is that of poking it with a stick. Both devices shown follow the same metaphor, the one on the left having a larger workspace. The user holds the handle, and the first joint of the handle is mapped to a point in the virtual environment. Whenever that point touches a virtual object, the device applies forces to the handle and implicitly to the user's hand. The Phantom is both a tracking device and a force feedback device, as it reports the position of the handle versus the bases to the VR application and applies forces to the handle when commanded. The response time is very fast due to the built-in motion tracking and to the actuation that avoids friction. Visible in the variant on the left, the device is actuated by stepper motors that thorough and ingenious use of cables rotate each joint without friction. The smaller variant on the right has only 2 motors, which are hidden in the casing. These devices can offer a very accurate exploration of the virtual environment, allowing the user to feel minute deformations of the virtual objects. They are often used in virtual sculpting, as shown in the image on the right, or virtual surgery simulations. Another category of haptic devices are haptic suits or shirts, meant to provide full body or upper body feedback. The fabric of the suit contains actuators that are commanded by the VR application to apply stimuli to the user's skin. The nature of the actuators embedded in the suit varies from vendor to vendor. Some use vibrating motors like those we saw used for tactile feedback, making the haptic suit in a vibrating piece of clothing that creates sensations in various skin areas. The length, intensity, and frequency of the vibrations can be used to simulate impacts or drag. The haptic shirt in the image on the left uses small currents applied to the user's skin to create sensations. This approach can become uncomfortable for some users and possibly dangerous for anybody having heart pacers or similar devices. Haptic gloves attempt to mimic the most common modality of interacting with the environment, through our hands. The task is very challenging given that hand interaction relies on 14 soft padded phalanxes and the palm, with tactile receptors all over the surface, many degrees of freedom, and the ability to use all or just some of them. To simplify the task, the haptic gloves attempt to simply provide force feedback at the fingertips. Like the Phantom devices, a force feedback glove is both an input device that provides information about the finger position and an output device that applies force to the hand. The finger position is determined by measuring the joint angles, 14 flexion-extension angles and 5 adduction-abduction angles. High-end gloves measure all these angles using piezoelectric bands applied over each joint, as seen in the image on the left. As the joint bends, the bands also bend and generate an electrical current with an intensity related to the angle magnitude. Lower-end gloves avoid measuring each joint angle individually, but rather measure an average finger angle. This can be achieved by using a longer piezoelectric material that is applied on the back of each finger along its entire length from the proximal joint to the fingernail. Using fiber optics is also a possibility, as bending the fiber affects the time it takes the light to travel from one end to the other. If the fiber is positioned as shown in the image in the middle, when the finger bends, it also bends to fiber. As light travels to the fiber from one end to the other, the finger flexion will influence its travel duration, and that can be used to infer a general finger angle. Such approach cannot differentiate between bending all finger joint uniformly, as when grasping an orange, and bending only the proximal joint while keeping the rest straight. Applying force feedback to the fingertips can be done either by pushing with a device mounted in the palm or by pulling on the fingertips with cables attached to a device on the back of the hand. The first approach prevents full finger flexion. The second device makes the users anxious at the idea that their fingers will be force bent backward. In both cases, the users carry a weight on their hands, which makes it difficult to keep their hands active and moving for extended periods of time. Walking in a virtual environment is a frequent task, most often done using indirect modalities like keyboard, mouse, or gamepad. Literally walking requires special equipment connected to the virtual environment that moves the avatar according to the physical steps taken by the user. The easiest solution is to use a treadmill as seen in the image on the left. While readily available, relatively affordable, and reliable, the classic treadmills limit the walking experience to a straight line on a flat, even surface. Simulating walking on an uneven surface is still a challenging research subject, while walking uphill and downhill is more approachable by tilting a treadmill or tethering the user and pulling or pushing to simulate the effect of gravity on slopes. The currently popular challenge is to allow the user to walk in any direction on an infinite surface, in other words, to create an omnidirectional treadmill. Several commercial devices provide such functionality, but as the device in the middle image, are rather large and bulky and not fit for consumer usage. Notice that walking on a treadmill while wearing an HMD raises a risk of falling, so users have support either by rails in the left image or harness in the middle image. The image on the right presents a lower-cost, smaller-sized device that allows a user to walk on a slippery surface on which, after stepping down, it is easy to drag the foot backward. This is only possible while holding to the rail or, in other cases, by having the user weight partially suspended in a harness. And finally, here are a couple of fun devices that allow the user to feel like flying. Unfortunately, the devices are too bulky for consumer usage. In both cases, the process of getting strapped in and starting the simulation most likely requires the assistance of at least one other person. The risk of nausea and dizziness is likely high on these devices. The goal of this chapter was to introduce you to the vast XR hardware ecosystem. There are devices, either commercial or prototypes, that address every human sense, those addressing vision and hearing being the most mature. Devices addressing force feedback are faced with solving a very challenging problem, and consequently most are still in prototype phases.